Okay, good evening, everyone. So, we'll start today's class. And as I mentioned in the end of the hello, anybody saying something? There any question?
Hello, sir.
Yeah, yeah.
Sir, regarding the midterm exam, can you just let us know the syllabus till up to what? The,
So, syllabus is going to be whatever we cover till the next lecture. Uh, so, Friday we are going to have the next lecture, right? So, whatever we cover uh, till then is the syllabus. So,
okay.
starting from the beginning itself.
Sir, anything about the pattern? So it will be problematic paper or something?
I mean, it is going to be a regular question paper. Problematic means I. So it's going to be subjective. It is not going to be kind of some
Okay.
multiple choice questions or something. It's going to be a normal question paper, and mostly it will be straight from the notes, right? So whatever I have covered in the classes, all these notes you have to just go through them, and most of it will be from there. Okay.
Thank you, sir.
Okay, so we'll start. So as we know that if we perform the image correlation process, digital image correlation process, so fundamentally what we achieve is the displacements of a point of interest, right? So if this is our point of interest and we want to track it during the deformation process, so we create subsets and then we create subset in a reference image. Let us say this is your reference image. In this reference image, you create this reference subset and then we do the correlation process for this subset in all the deformed images like this one and this one. And then from the correlation process, we get the moved locations of this particular subset here and here, right? So DIC process basically it gives you the uh, pixel coordinates, right? So we will only know that the movement of the subset or a point of interest in terms of pixel coordinates, right? Because we are doing the process in the images and images are having pixels, so that is why we call them we call it pixel coordinates. Okay, but that is not the ultimate aim. The ultimate aim is that we want to see that how what is the displacement in physical coordinates, right? So if I explain this camera imaging, which I have discussed already in the last class, but in brief, so this is the point where your camera is located, and this camera having some camera coordinate system. It will have its own coordinate system x, y, g, and then this camera is looking at some object like this in world coordinate system, right? And when you use the camera, you capture image. So whatever object you are having, finally you get the image in pixel coordinates, right? So you do the DIC process in pixel coordinates and you get displacements in pixel coordinates. Okay. But what we want to basically do, we want to go reverse. We want to go back to the world coordinate system where we'll have where the point of interest or whatever object you have will have their displacement in physical coordinates, right? Meter, millimeter, whatever. So we want to convert these pixel coordinates to the world coordinate system or physical coordinates. Okay. So this is the aim, to convert pixel coordinates of a point of interest to the physical coordinates or in world coordinate system. So to achieve this, we have to understand the process or transformation process from pixel coordinate to world coordinate system. Okay. So again, this is the another figure for explaining the same thing. So this is your object, right? Some object in the world coordinate system, right? And at on this particular object, we have this point, right? This is the point. Let us. This is the point L, right? And the coordinates of this point L are xw, yw, and gw in the world coordinate system. So these are the physical coordinates. Okay. So if you take this object and let us say on this cylindrical object you apply load both side, right? This is going to have a extensional deformation. So this particular point will move like this, and because of that there will be displacement in physical coordinates. So there will be displacement in physical coordinates. Okay, so in reality that is what will happen. You basically take a sample and you put that sample in a loading machine, and that loading machine will apply the load, and then because of the load the sample will deform, and during the deformation whatever point you select, that point is going to have displacement, right? So that happens in the world coordinate system or physical coordinate system. But when you are applying this DIC process, in the DIC process you take a camera and you keep that camera at some location, right? Let us say this is the location, okay, and this location is in camera coordinate system. So you have a coordinate system associated with the camera, right? So that is XC, YC, and ZC. Okay, and this camera is focused on the object. So this is the object on which your camera is focusing. So camera is going to give you the image, right? So within the camera, when your camera is focusing on the object and when it is taking the image, basically there is a film within the camera. So this is the image coordinate system, which is basically also the film. So within the camera, you are going to have a kind of a ball, or you can call it a film. On that film, the light will be getting collected. Whatever light is reflected by the object, that light is getting collected on that film, right? So this is the film. This is the 2D structure, 2D film, and this is generally in physical. It would have physical dimensions, right? So on this film, the light is getting collected, and that is how the image is forming. So that is how. So this film is having physical coordinates, right? So what you are saying that from world coordinate system to you are coming to camera coordinate system, and then from camera coordinate system you are going to the image coordinate system. So this is the process. So world coordinate system to camera coordinate system, camera coordinate system to the film coordinate system or image coordinate system. At the film, the image will form, and that image will be stored in your computer, and that is the final digital image. Okay, and in the digital image, you perform DIC process, and that gives you the displacement in pixel coordinates. Okay, so fundamentally, what is happening in this whole DIC experiment? There is an object in world coordinate system, and then you have a camera which is focusing on the object. So, and this camera is also placed in the world coordinate system, and that can be basically understood by this rotation matrix, combination of rotation matrix and translation vector. So if you have to understand the what is the location of the camera and the orientation, you have to basically find out this rotation matrix and translation vector. So with the help of this rotation matrix and translation vector, you can find that where the camera is locating in the world coordinate system. And then when you are in the camera coordinate system, then the other thing is you have to relate camera coordinate system with the film coordinate system. right? So that is the another transformation. So this is the first transformation, which is from world coordinate system to camera coordinate system. And then you have second transformation, which is from camera coordinate system to the film coordinate system or image coordinate system. And then once the film is formed on the once the image is formed on the camera film here, then you store the image in computer, and that is your final digital image. So you have to also see, you have to also transform the physical coordinates in the film to the pixel coordinates in the digital image. So this is the third transformation. So in total, in this whole DIC experiment, there are three transformations which are happening from world coordinate system to camera coordinate system. That is first transformation. Then camera to the film of the camera. That is second transformation. And then the film of the camera to the final digital image. That is the third transformation. Okay. So finally, I'll just again tell you the equation. So what you get from these three transformation is the relation between. So these are the relation xs and ys, relation of the these are the coordinates, pixel coordinates. Okay, these are the pixel coordinates in the image, in digital image. And these pixel coordinates in the digital image are related to xw, yw, and gw with the help of this equation. So we have these are basically two equations, right? And so other than xw, yw, and gw, we have other parameters which are the coefficients, and these coefficients like cx, cy, fx, fy, and then we have element of rotation matrix which are r11, r12, r13, and so on. And then we have element of translation vector tx, ty, and tz. So these are the coefficients which are basically relating pixel coordinates to the x. So x, w, yw, gw. These are the coordinates, physical coordinates in the world coordinate system of the same point. Okay, so this is the equation which is relating world coordinates to the pixel coordinates for a particular point, and this is through these coefficients cx, cy, fx, fy, and the elements of the rotation matrix and the elements of the translation vector. Okay, so we will see how to get this equation. That is what we have to understand here. Okay, so we'll start from basic terminologies. So first thing we'll try to understand is the pinhole. Okay, and the equation which we are getting here, this is coming through the pinhole, camera imaging, and other things. Okay, so we have to understand the fundamentally what we have to understand is pinhole projection model. Okay, this is the model, or this is in brief, this is basically pinhole model, which relates pixel coordinates of a point in the image to the real world coordinates in the world coordinate system. Okay, so first thing we'll try to understand is the what is the meaning of pinhole. So you basically consider there is an object in world coordinate system, and then you have a camera. So this is basically your camera. A particular camera in basic terms would have a pinhole here. So this is the pinhole, right? Through this pinhole, the light will be basically whatever light is reflected by the object. That light will be passing through this pinhole, and then on the back side of the camera, you will have this film, right? On this film, there will be the collection of light, corresponding to the object, right? And this collection of light is the basically formation of the image. Okay, so when the light is passing through this object, so this is the tree, right, in xw, yw, and gw coordinate system, right? So light coming from this tree passing through this pinhole here, and then it is making an image at the film of the camera, and you can see the light will be basically getting converted. That is why you get the inverted image at the film. So this is the inverted image of the object, right? Because of the nature of light which is passing. So this light is passing like this, and it's coming like this, and this point here is passing like this and coming here. So you get the inverted image at the film, and film is the at the back side of the pinhole, right? So this you can call the front, not front. You can call it the origin. This is the origin, right? This plane, which is passing through the origin. So, and here at the pinhole itself, right? So it's better to call this point as the origin. So pinhole is the origin where the light is basically passing. Okay, and this particular plane is the reference plane or reference. So this one you can call the reference plane. Okay, and then the film is passing. The film is forming on this. The image is forming on this film, which is basically at the back side of the pinhole, right? Back side of the camera. So this is the back side. Okay, so this is, you can call it front, and this is the back side. Okay, right? So do you get, since the film is at the back side, you get the inverted image. Okay, so let me just write that. So you get the inverted image. This is important to understand the inverted image funda, because use the we want to basically use the forward imaging model. To understand that forward imaging model, we need to understand what is the backside and how the inverted image is forming. So originally this is what will happen. This is your camera. This is the pinhole of the camera through which light will form. On the back side of the camera, you have the film. Okay, you can call it sensor film. This is generally in physical dimension. This will have some dimension, physical dimension, right? Okay, on this physical dimension film, the image is forming. Okay, so you can this can be any like 35 mm cross 35 mm, some dimension of the film on which the image is forming. Okay, so if you and the distance from this pinhole to the film is basically is the focal length, right? So this is how you define the focal length. Okay, wherever your image is forming, and whatever the distance from the pinhole plane to the film plane, that is the distance you call focal length. Okay, now if you take this film and then you basically move it to the front, so basically you are moving to the front side of camera, right? So okay, so this is how you are moving it at the same distance, whatever focal length you have, at the same distance if you keep it, then through this process, this is basically kind of a mathematical process. This is not the physical process. Mathematically, you can basically take the back side and then move it to the front side, move it to the front side at this particular location. And then when you move it to the front side, you will get the same image. So it will not be the inverted image, it will be the whatever image is there in the word coordinate system, that the same form will form at the forward or front side of the camera. The back side, you get the inverted image. Okay, so this is the, if you move your film to the front, in the front of the pinhole, that basically imaging model. So this is called some imaging model. Okay, so let me just write the complete name. This kind of, when you move the film to the in the front of the pinhole, This is called the forward imaging model. Okay. So this was about the pinhole, and then how you basically define the forward imaging model. So you are placing your film in the front of the pinhole of the camera, and the distance is going to be same, whatever focal length, whatever distance is there between pinhole to the film. At the same distance, you will move it to the front side. Okay, so this is also focal length, also focal length, same focal. And again, to understand it a little bit better, this is a better representation of the camera. So this is how you will have the. So this is the camera, right? Camera will have some access system. So the axis which is passing through the plane of focus, or uh, passing the center axis of the full field of view, is basically your optical axis, right? And this is the plane of focus where the focus of the camera is, right? Okay. And the main thing is the light is going to pass here, right? Whatever lights are there. Okay. Finally, the main thing which we have to understand is the film. The film which I was talking about is this film, which is which is at the backside of the camera. This is the film on which image will form. Okay. So all of these things are in physical dimensions. Okay. When the image is formed, when it is stored, then it's basically stored in the digital form, and that is in pixel coordinates. Okay. So this is the graphical representation of the same thing. So you have here, this is the point where your camera is located, and this camera is having XYZ coordinate system. And this is the optical axis. Optical axis basically perpendicular to the XY plane. So this is the XY plane, right? Perpendicular to the that XY plane in which the camera is placed, right? So camera will be placed in XY plane. So if you consider this, so XY plane is the plane in which the camera will be placed, and this is the pinhole. Okay. This axis perpendicular to the plane of placement of the camera is the optical axis, right? The other definition of this optical axis is this optical axis basically is perpendicular to the film. So this is the film of the camera. This is the film of the camera, by like I mentioned. So this is at the back side. So optical axis positive is in this side. The back side of this optical axis is the placement of the film of the camera. So if this is your camera, it is represented by the pinhole. The back side is the placement of film, right? And whatever distance is there between this. So if you do the 2D representation, so you can see this is the pinhole, right? Back side, this is the film. Okay. Give me 1 minute, guys. Can you hear me? Am I audible, guys?
Yes, sir.
Okay. Just give me 1 minute. Okay. Okay, so this whole thing, the 2D representation we are basically discussing. So, like I said, this is the point. This is the point, which is the pinhole representing the camera, and backside we have the film of the camera on which the light is getting collected, and the distance between these 2 points is the focal length. Okay, and the this optical axis is basically defined. Is the axis which is perpendicular to the film. Okay. So optical axis of the camera will basically intersect or is actually perpendicular or orthogonal to the film of the camera itself. Okay, and if you consider a point at which the camera is looking, let us say this point is M. From this point, you will see the light coming like this, and this will have a point forming here. So at this particular point on the film, you will have the light corresponding to this point, and that is basically M double prime. Okay, so when I was mentioning about forward imaging model or front imaging model, so this is the front imaging model. So what we mean by this is, so what you are doing, you are basically, so this is the location, pinhole location representing the camera. You are moving this film in front of the pinhole, and in front means to the positive side of the. So if you take this J axis, and this side it is positive, and the other side it is negative. If you place the film on the positive side of the G axis or optical axis, then it is basically your front imaging model or forward imaging model. Okay. The advantage of doing this is just a mathematical process. Okay, for the mathematical processing, not physical thing. So advantage is that when you are having this film in the backside, which is the physical case, physical scenario, you will see if the if your object is like this, you will have the inverted image, and that is why you have, if this is the x-axis of the camera and this is y-axis of the camera, you can see for the inverted image you have y coordinate downward and the x coordinate the other side. Okay, this is when you consider the film forming in the backside, which is the physical real case. But you can actually for mathematical processing, you can transform this film in front like this to the positive side of the optical axis, right? To the positive side of the optical axis, and the distance is going to be the same. Okay, so to understand it better, you can see this one. This is the pinhole of the camera, right? Backside you had the film. This is the optical axis. What you have done is you have moved it this side at the same distance, whatever distance was here, and then you can see that when it is the positive G side, you have the same film, and this is the point in the on which the camera is looking, and you will have the corresponding point on the film which is moved in front. And if this is having x, y coordinates, right, whatever coordinates, this will also have the same direction of xy coordinates. Okay, so this is the same. Basically, if x is positive for the camera here, then in this also the positive x will also be in the same direction. Similarly, if the y is in this direction for the camera, for the forward imaging, the y for the film will also be in the same direction. So it is for easy transformation from the camera to the film. Okay, so this is done. This is done for simple transformation from camera to camera's film. Okay. Okay. So now one more picture to explain the same thing. We have this pinhole here. This is the pinhole of the camera. And camera is having some coordinate system X, Y, G, right? This is the optical axis, positive side. Okay. So we have placed the film on the positive side of the optical axis of the camera, and then camera is looking at some object in the world coordinate system. But that particular point, so this particular point P0 is going to have coordinates in the camera coordinate system, right? So the X, this X, Y, and G, which is the coordinate system for the camera, right? And this particular camera is looking at some object, right? This is going to have whatever X, Y, G, right? So we have a point P0 for which we have the coordinates in camera coordinate system X, Y, and G. And then corresponding to this particular point, the light is passing through this pinhole, and it is corresponding to this. We have light, the collection of light forming on the film, right? This film will also have some coordinate systems. That coordinate system will be supposedly it is located here. Okay. So it will have some coordinate system. Okay. And the location of this coordinate system is here. So corresponding to this point P0 in camera coordinate system, we have a point Pi in the image plane coordinate system. So image plane is the representation of the film of the camera. So that's why this one you can call it image plane coordinate system. Okay, and for camera, it's camera coordinate system. Okay. So we have a point in camera coordinate system. Corresponding to that point, we have a point in the image plane coordinate system, which is Pi. So coordinates of Pi in image plane coordinate system can be related to coordinates of Pi in camera coordinate system. So there is a transformation here. Right? This is kind of a projection, and this particular projection is basically perspective projection. Okay. So if you want to relate the coordinates in camera coordinate system to the coordinate of a point in the image plane coordinate system, we can use the perspective projection model. Okay. So corresponding to this, so let me just write that this perspective. So we have from camera coordinate system to image coordinate system. Okay. This image is basically the film of the camera. Okay. Or you can also consider it like a retina of an eye, right? Okay. So this is all the physical thing which is there in the camera itself. So we are doing transformation within the camera, right? Camera is looking at something which is camera coordinate system, and within the camera we have the film, and whatever point at which the camera is looking, there will be a corresponding point on the film of the camera, and that particular point coordinates are defined in the image coordinate system or film coordinate system. And this relation transformation is basically given by perspective projection. Okay. So coming back to this one, so you can basically write the similarity of the basically triangle, right? So we have these two triangles. So you can call one triangle is this and the other triangle of this, right? If you use the similarity of these two triangles, you can basically write it as, so I'll write it here. So you can write, so this is the coordinate Ri, which is in image coordinate system for this particular point. So Ri, and the distance from this point to this point to the plane is basically f. So Ri upon f, we can write it equal to, we have Ro this side of this triangle and whatever distance is here, right? So this, let us call this at Z0. So we can write this Ri upon f equal to Ro upon Z. Okay. So this is the relations, popular relation we all know. Now Ri in image coordinate system would have xi comma yi, and Ro in the camera coordinate system, this one it will have again two coordinates. The perpendicular coordinates is z, here it is f. So two coordinates for Ro, the xy coordinate will be, can call it xo and yo. So this equation we can write, so we can write it also like this. So we can relate xy coordinate of this particular point pi to the xy coordinate of this particular point po. Okay. So this you can write as xi upon f, same relation I am using. So xi upon f equal to xo upon zo, and same equation we can write for y coordinate. So that is going to be yi upon f equal to y upon zo. So this has the xi comma yi, and here it is x0 comma y0, the xy coordinate, and the perpendicular coordinates are here z0, zo, and the f here. Okay. So this is the relation which we will use between camera coordinate system and the film coordinate system. Okay. So now we'll do the mathematical formulation of every transformation one by one. To do that, first thing we have to understand what are the transformations which are happening. So we have world coordinates. So we are considering a point in world coordinate system. World coordinate system. Okay, in for a particular point in world coordinate system, you will have, so that is represented by xw, and you can write it xw, yw, and okay, zw. So whatever point you are considering in world coordinate system or physical coordinate system, that is going to have three coordinates xw, yw, and zw. So we start from here, from world coordinate system, WCS, and then from world coordinate system to the camera coordinate system, which is located at the pinhole. Okay, so we have camera coordinate system, insert CCS. Okay, camera coordinate system also is basically in 3D. So this will have represented by XC. This will have XC, YC, and ZC. Okay. The transformation from world coordinate system to camera coordinate system is basically simple transformation, that is actually coordinate transformation. Okay, meaning that the transformation is simple. You just need to know what is the orientation of the camera in the world coordinate system and what is the location of the camera. That is represented by the rotation matrix and translation vector. So this is a simple coordinate transformation. With the help of these matrices, we'll be able to know what is the orientation and what is the location of the camera or this particular point in the world coordinate system. So this was the one, and then from camera coordinate system. So the next one is the from camera coordinate system to the image coordinate system, or let me write the film. Whatever film is there in the camera, so film or image or retina, whatever you want to call it, on which the image is forming. This would also have a coordinate system, so that's why the film coordinate system, film or image coordinate system. Okay, this is I'll call it IC. I'll use this. Wherever the image is forming inside the camera, that is the place I am basically I am trying to formulate, and for that the coordinate system is image coordinate system. Okay, in this one, this is a film or image or retina inside the camera is basically an 2D. This is a 2D object. So this is going to have 2D coordinates, and that we can basically represent as xi. It is going to have two coordinates, xi and yi. Okay. And then finally, from this film of the camera to the final digital image, and that so final you will have the digital image. Okay. That is your sensor in this particular technique. So this is the sensor. Okay, and that is why we can call it sensor coordinate system. Okay, so SCS. Okay, to write the kind of transformation we have. So from camera coordinate system, from camera coordinate system to the image coordinate system or film coordinate system, this is the perspective projection, which I just explained, perspective projection, and this is from 3D to 2D. Okay, this was also 3D. This is camera coordinate system, also 3D. Then when you are coming from camera coordinate system to the film coordinate system, you are basically now going from 3D to 2D. And this is a 2D object, so it's going to have xi and y coordinates. Digital image will also have pixel coordinates. So this is going to have pixel coordinates. Okay, and you can represent this. Let us say these are the pixel coordinates of the point and represented by xs and ys. So this transformation from the film of the camera to the final digital image is basically a simple, you can call it direct transformation. Okay, so this is the third transformation. This was the second transformation. Okay. So this is how the transformation is happening. So you have a world coordinate system in 3D, then camera coordinate system will also be in 3D, right? XC, YC, and ZC. Then camera to the film of the camera, that is a 2D object. So you are going to have 2D coordinates here. And then from the film 2D coordinates to the 2D coordinates of the digital image, which are in pixels. So this is the direct transformation from film to the digital image. Okay, so ultimately, if you write the transformations which are happening, we have RW, which is the world coordinate system in 3D, to camera coordinate system represented by RC. This is also in 3D, to film or image sensor of the camera, that is RI. This is in 2D. And then finally, we have the digital image, the coordinate system for that you can represent by RS. This is also in 2D. In terms of units, this is having physical coordinates. This will also have physical coordinates. This is also in physical coordinates. And this one is in pixel coordinates. Okay, the whole game is to relate these pixel coordinates in the digital image coordinate system to the physical coordinates in the real world coordinate system. Okay, so DIC is going to give you the pixel coordinates. So that is a known quantity. So once you are done with the DIC process, you know the pixel coordinates. The unknown thing which is here is what is the relation between these pixel coordinates to the real world coordinate system. And that is, I showed you one equation. That is what we want to achieve. Okay, so we'll do one by one. The main thing which we have to also kind of highlight here, you can see that the camera coordinate system is the key here, right? Which is basically the common element with respect to the world coordinate system RW and the other coordinate system. Okay, so you can basically you have this kind of relation. So camera represented by RC is having relation with the film and the final digital image, and camera is also having relation with the world coordinate system. Okay, so first thing which we have to determine the relation between whatever physical coordinates are there in the camera to the pixel coordinates, and then we will relate them to the real world coordinate system. So first, the mathematical formulation. Let me write this mathematical formulation. So first is from camera coordinate system CCS to image coordinate system ICS. Okay, and like I mentioned before, this is based on perspective projection. Okay, okay, so camera coordinate system, the coordinates for this are for a point, so this is XC, YC and GC, and the image coordinate system are XI comma YI. Okay, so using that perspective projection, we can basically relate here. So we can write Xi upon F is equal to Xc upon Zc. So let me just show it here again. Okay, so this is what we have. Now we are trying to relate. So we have this camera coordinate frame, camera coordinate system here. This is having XC, YC and ZC, right? For a particular point P in the camera coordinate system, right? So this is the point at which we are looking. This point is having coordinates in camera coordinate system, and corresponding to this point, we have the light passing through this particular pinhole, and it is forming on the image plane, right? So when we are talking about this point, so we have this point here, and the coordinates of this point are, if xi and y are the coordinate system for image plane, so this is the one which is basically having the coordinates. This is in xi and yi. Okay. So with the help of this perspective projection, we can use the similarity between this triangle and this triangle here, right? The distance from pinhole to the image plane is f, whereas the distance from the camera coordinate system to this particular point is zc, and the coordinates here are xc comma yc and gc, and this particular point here is having xi and yi. So that is how we can relate the x coordinate of this point in the image to the x coordinate of this point in the camera coordinate system. So that is how. So xi upon whatever distance we have f, right? So x coordinate upon this distance equal to x coordinate of this point, which is xc, and the z coordinate, which is zc. And then similarly for y coordinates, so yi upon f is equal to yc upon jc. So we have used the same relation, perspective projection, from camera coordinate system to image coordinate system. So for x coordinate, this is the relation. Then for y coordinate of the point, so yi in the image coordinate system divided by the focal length equal to yc upon jc. Okay, so we can write the coordinates in x coordinate in image coordinate system or film coordinate system is equal to f into xc upon jc, and the y coordinate of the point yi equal to f to yc upon jc. Okay, so this is, we have done the kind of transformation, and this is the form, these are the formulas which are basically relating xc yc gc coordinate in camera coordinate system to xi and yi. Okay, now the second transformation is from the film of the camera to the digital image. So that is the second one. So that means right, cameras film to digital image. This is represented by image coordinate system ICS, and this is digital image. This is represented by the SCS in pixel coordinate, right, in pixels. Okay, so like I mentioned before, this is simple direct transformation. Right, because this is in 2D and this is also in 2D. So what we are basically saying, in the back side of the camera you have this film, and that will have some size. So let us say this is the film of the camera. This, let us say this is the center point. Okay, this is the point where the optical axis of the camera will intersect, right? So that is the point where you basically assign the coordinate system for the film. So this is the point where the optical axis is intersecting. So that is how you basically decide the location or origin of the coordinate system. Okay, so for film, this is going to be xi and yi. Okay, so this is your film. So this is in physical dimensions. So physical dimensions it will have, or physical coordinates. So you can basically say camera sensor or camera film of, okay, some 35 millimeter across 35 millimeter, just to give an example. So this will have this some physical size. Now on this particular film, the light was collected, image formed, and that image was stored in digital form. In digital form, this is the digital image. So it would have, this is your image, right, which is the sensor. This will have the pixels. Okay, so these are your pixels. Okay, so just for the, so this is having pixel coordinates. You can decide, let us say 1024 pixel wise, 1024 pixel. This is the, for the example. So we have this image, digital image, which is having 1024 pixel in the basically 1024 by 1024 pixel square size of the image. Okay, so you have 1024 pixel this way and 1024 pixel this way, pixels this way. Okay, and if you do transformation, so if you take a point here, right, point pi, this will have coordinate in the physical film. And then if you take some point in the image, let us say this is your axis and this is your ys. If you like we mentioned here, right? So the digital image, the pixels are denoted by the coordinate of the pixels are denoted by axis and ys. And the for the physical film you have xi and yi. Okay. So this particular point in the film having xi and yi, then similarly it will have location here. Okay, and that will be coordinate axis and ys. Okay. So you can do direct. So this is direct transformation. Okay. So direct transformation means that you can basically just have a relation between, you can just have a relation like um, if 35 millimeter is the size this way, right? And the image is of 1024 pixels. So you can basically have a relation between millimeter and pixels. So you can basically say how many pixels per millimeter. If you are considering, generally the size would be in small. The film of a particular camera will be of a small size. That's why millimeter is the dimension or unit I have considered. So ultimate thing is to just do the transformation from film to digital image. You need to know how many pixels per millimeter. If you know that, you can basically decide based on the xy coordinate. You can go to digital image and find the pixel coordinate. Okay, but so there is one thing we have to consider here, that um, the uh, the thing is that the each pixel, right, whatever pixels we have here, each pixels uh, would have the physical size, right? Physical size, right? So you can say 1 micron or 10 micron meter size of a particular pixel. So every pixel in reality will have a size. So that comes from the relation between millimeter and pixels. Okay. The other thing is uh, the pixels may be rectangular. Okay, maybe rectangular. So they may be like, so a particular pixel may be like this square. The meaning is that whatever size, if it is a square pixel, this will have same size in millimeter. The same size in both this direction and this direction. If it is rectangular, something like this, let us say this is rectangular pixel. So this dimension will have higher in terms of the physical dimension, higher dimension, and this is lesser physical dimension. Okay. So the problem with because of this is going to be that the pixel density, if you calculate from here to here, so if you calculate pixel density in x-axis, so pixel density in x-axis, this is your x-axis, will be different from pixel density in y-axis. Okay. So if the pixel is of rectangular form, this will create different pixel densities in the digital image. Okay, most of the time it is square, but if this is the case, if the pixel physical size of the pixel of a particular pixel is of a rectangular form, if the shape of the pixel is a rectangular form, then it is going to have different pixel densities in digital image in both x, s, and y, s directions. Okay. So now we have to basically find different pixel. If the pixel densities are different, then we have to find the relation. So whatever relation we have between millimeter and pixel, they will be different in both x and y direction. So let us say the SX is the pixel density in x direction, and similarly let us say SY is the pixel density in y direction. Okay. So we can now, with the help of these pixel intensities, we can pixel density values, we can relate millimeter with pixel. So what I'm saying is you can basically write uh, xs, which is in which is in pixel coordinate, which would have pixel coordinates, equal to sx into xi. Okay, so x coordinate in the image coordinate system to x coordinate in the pixel coordinate system. So this is the physical coordinate and the pixel coordinates. With the help of pixel density in x direction, this one, we are able to relate pixel coordinate in x direction to the physical coordinate in the x direction in the image coordinate system. Okay, so this particular axis is having relation with xi with the help of pixel density in x direction. Similarly, you can define the relation for the y coordinate, which is y coordinate in pixel coordinates. So y s in digital image is equal to, you can basically make use of pixel density in y direction, that is sy equal to xy. Okay. uh, Sorry, so this is basically yi, right? Okay, now we have a relation between, so going back to transformation, so now we have a relation between the film coordinates of a point to the digital coordinates in the image. Using this direct transformation, we are simply making use of pixel densities in x and y direction. Okay, so since we have xs, the pixel coordinate equal to pixel density in x direction equal to xi, and then we have ys, which is pixel density in y direction, and then we have coordinate in y direction in the image coordinate system. Okay, and we already have a relation between xi. So relation between CCS, camera coordinate system, and image coordinate system was, so this was xi equal to f xc upon zc, and yi was f equal to yc upon jc. This relation, which we can basically insert here. So what we have, xs equal to so we have xs equal to sx into f xc upon zc. Similarly, ys equal to sy into f yc upon jc. Okay, so this is the relation. This is the relation between. These are the relations between sensor coordinate system or digital image and camera coordinate system. So relation between sensor coordinate system or digital image and camera coordinate system or camera. Okay, so we are able to now relate pixel coordinate in the digital image to the camera coordinates xc, yc, and gc. Okay, so one other thing which we have to add here. right now what we mentioned that this is the point in the film coordinate system, right? And corresponding to this, we'll have a point in the digital image. But it is basically for processing in digital images, it's better to take the origin of the digital image here at this corner. So you can basically have axis here and y as this direction. So if this is the origin, then we can basically whatever coordinates we have for this point from this transformation, we can translate that to if you put the origin here. So this particular point, you can have a coordinates for this particular point. So this is, let us say the coordinates of this point corresponding to this point going to be cx and coordinates cx and cy. Okay. Now we can translate this coordinate, whatever coordinates we achieve for this, we can add these coordinates and then we can basically say, let me just write it and then it will be easier to understand. Okay, so what I'm trying to say that this is your digital image. If you have your origin here, xs and ys, this is the point, and let us say this is the point which is coordinate of cx and cy. Okay. We can whatever point, this is the point of interest. Let us say this is in digital image ps, and let me again, this is your film, right? In the film, this is the point where optical axis of the camera g axis will intersect perpendicularly. So this is the coordinate of xi and yi, right? Corresponding to this point, we have these coordinates in the final image, which is digital image. Okay, and then let us say there is a point here which we are trying to track, and this is the point pi, which would have coordinates xi comma yi, right? So from direct transformation which we have done here, what we actually achieved that xs is related to, so this is the point in the digital image which is will have xs comma ys. So xs, these coordinates are related to this coordinate with the help of pixel density. So xs was pixel density in x direction into xi, and ys was pixel density in y direction sy into yi. Now if you had the origin here, in the digital image, these equations are fine. If you are moving the origin from this point to this point, then you have to simply add these coordinates to find the coordinates of this point. So finally, if the origin is here, if origin at the corner left, let me just write it properly, at left top corner, in that case the pixel coordinates are now axis will be cx plus whatever we have here, that is sx xi, and then ys will be cy plus sy yi. Okay. And using the relation, this one, we have a relation between x and xi yi with the xc yc and gc with the cameras. So finally the equations, so we know using camera coordinate system and image coordinate system relation, which is, let me just write that. So let me just write these equations first. So xs is equal to cx plus xi sx xi, and ys is equal to cy plus pixel density in y direction, y coordinate in image coordinate system. The relation here is xi is equal to f xc upon zc from perspective projection, and yi was f into yc upon gc. Now these relations we can insert here. Finally, we have xs equal to, we have cx plus whatever, so sx f xc upon zc, and ys equal to cy plus sy f yc upon dc. Okay, now in this equation, if you take sx is the pixel density in x direction, and then the focal length, both of these parameters are constant parameters. Okay, and similarly this one sy and f, this is also, both of these are constant parameters. Okay, so you can basically combine both of these, so you can write sx into f, both of these are constant parameter, equal to fx, and this particular parameter is called focal length in x direction. And similarly you can write sy into f equal to fy, this is focal length in y direction. Okay, to repeat, sx is the pixel density, that is a fixed parameter for a particular camera, whatever camera you have. For that particular camera, the pixel density x direction and pixel density in y direction is a fixed parameter, or it's a camera parameter. Similarly, the focal length for a particular camera is also a fixed parameter. That is why you can basically combine these coefficients and define a new parameter. So that is why we have fx, which is the multiplication of pixel density in x direction and focal length, and then you have fy, which is the focal length in y direction, is equal to pixel density in y direction into f. Okay, so with this simple modification, finally the equations are x is equal to cx plus fx xc upon zc, and y is equal to cy plus fy yc upon jc. Now we have obtained the relation. So this is the relation, these are the relations, between camera coordinates and the digital coordinates, digital or pixel coordinates. Okay, in this the other parameter, so fx fy I have defined here. So fx is the focal length in x direction, fy is the focal length in y direction. These are camera parameters, and similarly we have here cx and cy. These are, so these coordinates are also camera parameters. Okay, these are also kind of fixed parameters. So cx, let me just, so both of these are called principal coordinates. Okay. So now to summarize this, what we have, the relation between camera coordinates and the pixel coordinates are related by fx fy and cxy cy. So fx fy cx cy, these are the constant parameters, these are camera parameters. Okay, these are the camera properties. The moment you have the camera, you will know these parameters. Okay, so these are camera parameters. The other name for these parameters, it's actually called, this is intrinsic parameters. Okay, These are called intrinsic parameters. These are camera parameters, or these parameters like the inherent property of the camera. Okay, and with the help of these intrinsic parameters, you are able to relate the pixel coordinate in the digital image, to the XC, YC, and ZC, the coordinates in the camera coordinates. So if we go back here, we have now basically found the relations of this part, where your camera coordinate system is related to digital image coordinate system. I mean, a sensor coordinate system or pixel coordinate system. In between, you have the film coordinate system. So we have done this part. Now we have to basically find the relation between world coordinate system and camera coordinate system, right? So we have to find the relation, like I mentioned before. These are, if you have to find the relation between world coordinate system and camera coordinate system, this is simple coordinate transformation, and this is the combination of rotation, matrix, and translation vector. Okay, so we'll do this part in the next class. So we will find the relation between uh, camera coordinate system and world coordinate system, and then we'll be able to, then we have already have the relation, we have already obtained the relation between camera coordinate system and the digital image coordinates, the image coordinate system or camera coordinate system. Finally, we will basically relate all of these parameters. Okay. So if there is any question, please let me know. Otherwise, we'll stop here. Okay. So uh, we have obtained the relation between the camera coordinate system and the pixel coordinate system. The other part which is remaining is the basically this part from world coordinate system to the camera coordinate system. This part, once we are able to obtain this part, then we'll be able to close the gap, and then we'll have the final equation which I wrote here. So this is the final equation which we'll obtain, and then we'll extend this equation, because all of this is happening for a single camera, right? We are still talking about a single camera looking at a point in world coordinate system. But if we are interested in 3D DIC or proper 3D measurement or 3D displacement measurement of a particular point, single camera won't be enough. Okay, because you can see the known coordinates are pixel coordinates. This will come from DIC process. Okay, and all the other coefficient like CX, CY, this now you should be able to understand what I'm talking about. So CX and CY are the principal coordinates. Fx, Fy are the focal lengths in x and y direction. These are camera parameters or intrinsic parameters which we have already obtained. When we do the transformation from world coordinate system to the camera coordinate system, we'll be able to formulate and obtain the rotation matrix elements and the translation vector. So all of these are your coefficients. The unknown for a particular point. So this is the point we are looking at. So for this particular point, in reality, there are three unknowns: xw, yw, and gw. So we have three unknowns. Okay, and what we have two equations, right? Which is basically, so we get two coordinates from the image. So basically, we have two equations. And three unknowns. So this basically says that a single camera will not be able to provide us the information for 3 unknowns or 3 x, w, y, w, z, w coordinates. To solve that problem, we have to use two cameras in stereo vision configuration. Like human eye, our eye system is basically we have two eyes which are configured in stereo vision configuration, and that is how we are able to understand or we are able to perceive information in 3D and 2D both. Okay. So similar to that, we have to add one more camera, camera 1 and camera 2. From both of these camera, we'll get for camera 1, we'll get the similar equation. Camera 2 also will get the similar equation. Okay. And then we need to basically see how to achieve these equations. And then with the help of two cameras, we will be able to find 3D coordinates of a particular point in world coordinate system. So we'll try to understand this one. So we'll first finish the formulation of all the transformations, and then we'll talk about 3D DIC. And then we will see, finally we'll see that we understand that single camera will not be able to give us 3D coordinates or XW, YW, GW, but a single camera can give us uh, two coordinates for a particular point, or in other words, single camera will be able to help us to do 2D measurement or in plane measurement. So you can say a single camera won't be able to give the G coordinate, but we'll be able to if the displacement is in plane, not out of plane. In that case, a single camera will be sufficient to perform in plane measurements. Okay, all of this we'll understand in the next class, and then that will be the end of digital image correlation technique. Okay, so I'm going to stop here and see you in the next class.